Hello class. This lesson is going to be your lesson 2 of Physics Unit 1 Primer Worksheet, and it's going to be covering the second law of thermodynamics. The first law states you can't win. The second one states you can't even break even. Now the definition of the second law of thermodynamics states that disorder in the universe is always increasing. The term for that is entropy. Because disorder, another word, it would be less organized. And entropy is saying that it's less organized, there's disorder. And this leads to the change of energy. And remember, energy can be abbreviated with just E. And it changes energy into a less usable form. And that's where you get the can't even break even part. Usable form. So remember, entropy, less organized. Disorder, kind of like 7th graders tend to be less organized. So anytime motion occurs, or another word, work, thermal energy goes into a less usable form. And that's the definition of the second law of thermodynamics. And now we're going to focus on temperature. And temperature can be found in your textbook on pages 274 through 279. Now, what is the relationship between temperature and kinetic energy? So temperature is the measure of the energy in a substance. Is the measure of the energy, capital E, in a substance. And what it's actually measuring is it's measuring the average kinetic energy of the particles. And remember your unit on states of matter? You talked about how everything's made up of particles. Now, what it's measuring is the average kinetic energy of those particles. Those particles are constantly moving. It may not look like it, but that's what temperature is doing, is it's measuring the average kinetic energy of particles. So when you look at temperature, you have to look at thermal expansion. So what is thermal expansion and how does it relate to how a thermometer works? Okay? So thermal expansion is the increase in volume of a substance and how of a substance as temperature increases. Because the liquid in a thermometer expands at a constant rate we can use it to measure temperature. And remember, this is looking kind of at temperature. This is looking at Charles' law. So remember, in that states of matter unit, you found out that when things increase, it expands because those particles are moving really fast and they get farther and farther apart. So what a thermometer does is that it puts lines at specific key temperatures that it knows that that liquid should expand to at that temperature. So that's how we're able to know what the temperature is, because the liquid will expand, or I guess shrink up, and we can tell what the temperature of the air is considering that liquid. All right, and that deals with thermal expansion. So an example of thermal expansion would be expansion joints and how we use these in real life. These are real life applications. So expansion joints and thermostats. Right? Expansion joints and thermostats. And how expansion joints help us is what expansion joints are is they're put in bridges, all right? And when bridges get really warm, the concrete on the bridges can expand, because that's what the particles do. And if they expand far enough, they can break. So what we do now is we put these expansion joints in the bridges so that it allows the bridge to flex and expand without the bridge breaking. And how thermostats work is there's a bimetallic strip, and you're going to see this in your demos. Bimetallic strip, and the strip allows the strip flexes with changes in temperature, and that's how it allows the temperature to increase or decrease depending on that strip. Okay, and like up above thermometers, we use mercury. We used to use mercury a lot, and now it's somewhat of an alcohol, because mercury is very dangerous. So that's the liquid you usually use in the type of thermometers nowadays. All right, so there's 3 temperature scales that we look at. All right, Fahrenheit is the first, and that's what you'll see when you watch weather channels and things like that. It gives the temperature in Fahrenheit. And then Celsius is what we use a lot more in science. We do not use Fahrenheit in science, we use Celsius. And Kelvin is another form, or is another scale. And now Kelvin is the SI standard unit for temperature. But mainly we use Celsius because it's easier to use in science. 0 is freezing, 100 is boiling. It's a lot easier to use. And there's a way to calculate between Fahrenheit, Celsius, and Kelvin. But you'll see a lot of science in Celsius. Kelvin is a standard unit. Now, absolute 0 is negative 459 degrees Fahrenheit. And this is the temperature at which all molecular motion stops. And the third law of thermodynamics, which we're not going to really talk about, this is what it's about. The third law is about absolute 0. But we don't talk a lot about it because we've never been able to reach it. Never reached it. Okay? And with absolute 0, this is the things we're talking about with cryogenic freezing, where you're able to freeze something and the particles aren't to move, and then be able to bring it back later in life. And this is impossible because entropy is exactly zero. This means there's no disorganization, and that's just very hard to reach because, like I said, everything's made up of particles, and those particles are constantly moving. We've come down very, very low to absolute zero, but we've never reached it in a laboratory. Okay? So the next section we're going to be looking at is what is heat? And this can be found in textbook in your pages 280 and 287. So you can look there to see what is heat. And now heat, a good definition, is the transfer of energy between objects at different temperatures. I'm going to abbreviate temperatures because I'm running out of room. Okay? So make sure you take note of this. It's very important. Heat is always transferred from warmer objects to cooler objects. Right? So heat is always transferred from warmer objects to cooler objects. The heat is leaving into cooler objects. Heat is thermal energy. And we talked about thermal and energy in lesson 1. And variables of the thermal energy are temperature, and the amount of substance. So if you have a small bowl of soup in a huge pan of soup, there's going to be more thermal energy in the huge bowl of soup because there's more of that substance. Okay? Heat is transferred between objects until they reach thermal equilibrium. Can get rid of this and. I don't know why that's there. But equilibrium. Okay? And this is what it means is same temperature. So it's going to keep transferring until what feels hot to you feels the same as what feels cold to you. Okay? So that's about the transfer of heat. Okay? All right, so now that we've talked about heat and thermal energy, we're going to talk about methods of transferring the thermal energy. Okay? So one method of transferring thermal energy is conduction. And this is the transfer of thermal energy via direct, come on, direct contact. All right. So that's like a pot on the stove. That burner, when the pot hits the burner, that's transferring the heat through direct contact. And what you're looking at is conductors equals good energy transfers versus insulators equal poor energy transfers. And the insulators kind of inhibit the transfer of energy. Okay? So a pot on the stove would be good conductors of energy transfer. Okay? And there's a table on that in your book, good conductors versus poor conductors. Okay? Another method of heat transfer is convection. And this is the transfer of thermal energy by the circulation of a liquid or gas. Okay, and an example of this would be you heating up a pot of water on the stove. Now, the pot in the burner would be an example of conduction, but since the water, it's a liquid, and you can see the circulation, this would be an example of convection. Okay, convection current is a circular motion created when gas or liquids are heated and particles have different densities to their temperature. So the pot of water, going back to the pot of water, the hot water on the bottom that's getting heated right away is going to rise up really fast, and that's where you kind of get that bubbling. But then once it hits to the top of the water, it's going to sink down because it's cools down, and the low density water goes to the bottom. But the hot water, which is a higher density,
55422. Mr. Greenwood, please call the main office.
will rise up. And that's where you can see that convection current, the rising and the falling. Okay? And the third method of transferring thermal energy is radiation. Okay? And radiation is the transfer of energy as electromagnetic waves. All right? This type of energy can travel through empty spaces as well as through particles. As well as through particles. And electromagnetic waves can be written as EMW. Okay? And those are infrared invisible light. And those can be found, a good example of that can be found on page 284, figure 7. Okay? And an example of this would be a sun. We get a lot of heat and thermal energy from the sun. All right? And that's the sun, it goes through the empty spaces, and then it goes through our particles in our atmosphere, and it warms us up with its infrared waves, and that's why we feel warm, because of the sun. All right? All right, thermal conductivity, the definition of that is a physical property that identifies how well a substance conducts thermal energy. Okay? So that's what thermal conductivity is looking for. And like from above, this is what we're talking about with insulators and conductors. Okay? So like an example of this, seeing thermal conductivity would be when you go in a car and it's really cold out. You feel the cloth seatbelt, and it doesn't feel that cold because it's an insulator, but then you feel the metal piece that goes in and connects it, that feels really cold because metal is a great conductor. So that's an example of thermal conductivity. Now, another term would be specific heat. Specific heat is the amount of heat needed to change the temperature of 1 kilogram of a substance, could be water, by 1 degrees Celsius. All right? Okay? And a high specific heat would equal a poor conductor. And a table of all the specific heats can be found on page 285. Okay? And there you'll see that water has a very high specific heat. And that's because water is a poor conductor, believe it or not. The only reason why it conducts electricity do so well is because of all the particles usually found in water. But water is very high specific heat. That's why at night you can go down to the lake in the summer and you can see kind of steam rising off of that, because the water takes a long time for it to cool itself down, and it usually feels it can be colder at night. But during the day, it's hotter at night, and then during the day it feels colder because the water takes forever to change temperature. Okay? Then that deals with specific heat. Now we're going to be talking about matter and heat. And matter and heat can be found on textbook pages 288 and 291, like that. All right? Now, what are 3 variables that affect the state of matter a substance is in? Okay? One variable is particle attraction. How attracted those particles are made of, or are, that make up everything. Particle attraction. Another variable is particle speed. And a third variable is pressure around them. And those go back to Charles' law, okay? Because that deals with pressure. So you really have to look at what the particles inside when you're dealing with states of matter, okay? When ice is at 0 degrees Celsius, added energy is used to melt the ice. Not increase the temperature. However, once all the ice has melted, the added energy will increase the temperature. And a great visual for this is figure 3 on page 289. And you can see that. And basically what it's saying is, remember the chart where you add your energy, or energy is on the bottom, and then degrees Celsius is on the y-axis, and it starts off like this, and then it spikes up real quick. And that's because the energy is going in to melt these particles right here, and then once they're all melted, then the temperature can go up, okay? The temperature can go up once all those particles are melted. And that's why the states of matter, it's particle attraction, particle speed, and then the pressure around them are all variables. Okay, chemical changes release or absorb thermal energy when breaking or forming bonds. An example of this would be burning wood. Because chemical changes absorb or release that thermal energy, and that's why we feel warmth when burning wood. All right, and the unit of energy in food is a calorie. And many of you have heard this word and seen this word because it's found in the labels of food. So you should be familiar with that. And a calorimeter is a device that measures energy changes by measuring heat. And when we talk about this, we're talking about it, and it's used to calculate the energy in food. Okay? And an example of and another example would be a bomb calorimeter. And what that does is it calculates the energy in the food by burning the food and seeing how much heat is given off from it. Okay? So this is the end of the lesson 2, second law of thermodynamics. And basically, it's just showing that you cannot break even. Thank you for listening.